A very good morning, good afternoon, and good evening, everyone who have joined us. I'm Chanchal from marketing team of Tata Lexi, and I'll be your moderator for the day. It is great to see how many of you have joined us today, and I take this opportunity to welcome you all to the Autonomous Off-Highway webinar conducted by Tata Lexi. I hope everyone is keeping safe and healthy amidst this pandemic. As we all know, the autonomous technology will create a great leap in the off-highway segment, especially for construction, mining, and agriculture sector. Perception accuracy for object identification and prediction in work sites, mines, agriculture areas is extremely critical in autonomous off-highway vehicles. Today, we have with us Mr. Rajesh R., Senior Architect, and Dr. Anjana Pitas, Specialist, both from Autonomous Practice of Tata Lexi. They will give us insights on the requirements, challenges, and solutions for perception and localization of autonomous off-highway vehicle. We encourage you all to ask plenty of questions during the session. At any point, please type your questions into the chat box that you can find on the screen. I would request you to enter your name rather than posting anonymous questions so that if any discrepancies and if you want to reach in future, that would help us. At the end of the presentation, your questions will be taken by the speakers and will try to answer as many as possible. Rajesh and Anjana, it is a pleasure to have you all with us today. And I welcome Dr. Anjana now to take control and begin the session.
Thank you, Chanchal, for the introduction. Let's move on to the discussion. This webinar is organized mainly in 5 sessions. First, we are going to discuss about the global market trend and the use cases. Then the challenges associated with the use cases. Then the challenges with the development activities. Finally, the solution, concepts, and approaches we have. All the content is blended with the learnings we achieved from various ongoing and completed projects and the research and development activities we are carrying out in Tata Lexi. Moving on to the overview of Tata Lexi. Tata Lexi is an integrated design, engineering, and technology-based company headquartered in Bangalore. We do consumer research, technology consulting, product design, development, testing for various industry sectors like transportation, media and communication, and in medical electronics. This is enabled through a core team of 8,000 plus engineers and technologists who work from different locations in India and service our global clients. In transportation, we work for last 25 years and bring together world-class embedded mechanical testing, AI analytics, and IoT practice, and we have an award-winning HMI team backed by a SPICE process. With these enablers, we are driving solutions for connected, autonomous, shared, and electric vehicles of the future, which even includes construction and mining vehicles, farm equipments, personal and commercial vehicles, and we are even in rail sector. Let's have an introduction. As we know, the operator assistance and self-driving solutions for off-road segments such as farming, mining, and construction equipment are completely distinct from those of road vehicles. In the case of road vehicles, we have a specified road lane markings, traffic signals, traffic signs, and the infrastructure is well equipped. But it is completely different from those of off-road vehicles. There won't be a proper road, there won't be any traffic signs or signals, and vehicle is supposed to be operated in farm field, construction sites, mine sites, those kind of uneven terrain. So this unstructured environment, the impaired vision, increased degree of freedom of operation of vehicles, all necessities complex solutions. And hence these autonomous vehicle development efforts in this sector, worth billions of dollars, are beginning to yield mature systems in production. Coming to the global market trend of off-road vehicle segment. Let's have a look on to the major studies from major industry experts. From this, it is very evident that autonomous construction equipment are all set to change the dynamics of construction industry and projected to grow with a CAGR value of 28.7%. This is the forecast report from the period 2018 to 2026. And this is even applicable for all the domains like the agricultural, construction, lawn and healthcare, material handling, and even in all the sectors it is addressing. When we look a little more deep into the autonomous machines, that means the expected market uptake of autonomous machines. Here also we can see a significant impact from 2020 to 2030, especially in the adoption of use cases we are planning to discuss today. The first case is the workers operating in, supposed to be operating in construction and mining sites. For example, vehicles like autonomous dozers, excavators, load carriers, and halters. These are supposed to be operating for excavating and grading kind of operations in construction sites and mining sites. And these kind of vehicles are, in some cases, they are often connected to perform coordinated actions. And terrain mapping and visualization in these scenarios bring many complexities in their autonomous operation. Another case is the support in agricultural activities. That means the vehicle is supposed to be support to perform actions in agricultural activities. And here also we can see a research study that autonomous farm equipment market will be worth 150 billion US dollar by 2031. And these kind of vehicles are not only supporting in the reduction of manpower, but it enhances safety and precision in their operations. And these multiple machines, manned or unmanned, can even coordinate and perform operations in a field to accomplish the task in a very cost-effective and time-effective manner. And we can see another study that is from National Agricultural Tractor Safety Initiative in US reports that tractors cause about 130 deaths annually. Here comes the importance of bringing operator assistance solutions. And toppling prevention is an example of operator assistance solutions in tractors. And another support is for hitching the trailer, the trailer hitch. We know that parking a vehicle which is attached with a trailer is a challenging task even for a well-trained driver. And yes, the trailer hitch assistance and autonomous trailer hitch is right around the corner. Then coming to the challenges associated with the use cases. Depending upon the mode of operation of these vehicles, one major issue they are facing is the degraded visibility. Why? Because the environment is continuously changing, and the environment can experience challenges due to dust, fog, rain, and low light conditions. All these conditions demands high resolution cameras, infrared cameras, and high cost lidar sensors and all. Another factor we need to consider in the development phases are the impact of weather on perception solutions. We know the different kind of weather conditions can affect the performance of sensors, like it may cause poor visibility, lower range, it reduce the range, the field of view and range, and it may cause reflections and shadows in the capturing images and point cloud data. So in some cases, ruggedized enclosure and other cleaning mechanisms are required in order to protect sensor from uh, the weather, I mean the impact of weather. Another important issue is the challenges due to unstructured environment. For example, consider the case where the vehicles are supposed to be operated in mining sites. We can't expect a continuous GPS signal all the time in construction, I mean in mining sites. The GPS satellite signals may be corrupted by data noise, multipath errors, clock errors, or atmospheric delays. In other cases, depending upon the site where the vehicle is operating, it is very difficult to represent the boundary of drivable region in some cases. And another is since the frequently changing dynamic environment demands the frequent update in map process, it again creates overhead in computation. And other issue is the vehicles experience errors in odometric sensor due to the wheel slip and all. All these complexities brings very big challenges in mapping and localization process. Another factor is the mode of operation. That means these vehicles are supposed to be operating in extended range, I mean extended reach, especially excavators. The operating area, I mean depending upon the mode of operation, extended range of activity is required for excavators most of the time. And the operating area is invisible for sensors mounted in and around the driver cameras, especially in cranes and excavators. Those who have long arms and operational area will be very wide up. Other issue that is the sensors attached in the moving parts of the body. Since the vehicle is completely different from that of the on-road vehicles, it has a periodically moving parts in the vehicle. For example, in the case of excavator, its arm and bucket is continuously moving for its grinding, loading, and loading kind of activities. So the sensors which are attached with the bucket and boom may experience interferences and noise due to this motion of parts. And in some cases, the companion vehicles, I mean the companion vehicles like drones are required to capture the environment correctly. The sensors will be attached with the drone, and the drone and the operating vehicle is in coordination for the navigation operation, and the image or the data, I mean the point cloud data captured by the drone will be transferred to the vehicle for its autonomous navigation. Another commonly using solution for handling this, uh, I mean the sensors attached in the moving parts of the vehicle is the combination of static and sensors, static and moving sensors. That means, as I said earlier, in the case of an excavator, the bucket and arm will be in periodic motion, and their frequent movement is very high compared to the moment of boom. Boom is having less movement compared with the arm and bucket. So the case like the sensors attached with the bucket and boom can be in continuous motion, and that in the boom another part of the vehicle will be we can consider it as a static sensor. So here comes the complex fusion techniques to merge the data captured from camera and lidar sensor. Mostly lidars and cameras are suggested for these purposes. So here we need complex fusion techniques, and eventually we will get the composite view of camera and lidar data. Yeah, another sensor, the requirement is IMU sensors. That means the inertial measurement units. This is commonly used for tracking the movement of sensors. And the accelerometers and the gyroscopes in this IMU unit help sensing the movement of the vehicle and the vehicle parts. And we will get the measures like acceleration and angular velocity. And the position data or the angle information of the joints of the vehicle can also provide the information for tracking the movement of sensors. Another factor which we need to consider is, how to handle the varying field of view of sensor. As I said earlier, for example, the case of vehicle like excavator, when we look on to the mode of operation of these excavators, they are meant for doing the external reach kind of operation. And since the sensors are attached with the moving parts of the body, moving parts of the vehicle, it experiences a continuous variation in their field of view. So that has to be handled, that has to be tackled in the development stages. And this figure illustrates correctly how how the field of view is varying when the sensor is attached with the arm or boom of the excavator vehicle. These sensors cause the coverage of sensor to change from frame to frame. And the lower position of the arm, the coverage of the on the terrain will be very less, but the resolution will be very high. These kind of behaviors of the terrain data are more complexity, and we require sensor fusion techniques for combining, for getting at the correct view of the environment, the terrain. Yeah, this another thing is most of the cases, since as I said, it experience vehicles like excavators experience a varying field of view. We are getting the data with mostly with a varying field of view, and in order to fit those data to the required grid or the required map, in most of the cases we need extrapolation or interpolation kind of interpolation of data. Yeah, in some cases, we need the not trying. In some cases, not just doing a simple extrapolation. We need some intelligent data filling or data augmentation kind of approaches for doing these kind of operations. Yeah. Next is the problem of data storage. In order to handle the broad and wide range of field of view required by the operation of these off-road vehicles, it requires bigger storage. A huge amount of terrain data is to be stored and processed before their maneuvering, which requires higher storage for computing platforms. Then moving on to the development of solutions and challenges. This session will be handled by our senior system architect, Rajesh R. Over to you, Rajesh.
Thanks, Anjana, for the points on the use cases and associated challenges. Hello. In this part of session, we will discuss on the challenges associated with the development activities of solutions for the off-road segment. Artificial intelligence-based solutions requires huge amount of data sets for the development phase. Data collection from the real field is challenging and a costly affair. Hence, synthetic data generation using simulators is a preferred way to proceed for the initial phases. SEGO, Blender, and Unreal Engine simulators are used for the dataset creation. Many cases, due to the operating conditions, camera images are not dependable for the object detection and classification. The solution has to use the point cloud data from LiDAR. The varying resolution of the point cloud is a real challenge faced by the detection algorithm. Depending on the distance of the objects and the resolution of the LiDAR, there will be variations on the point cloud density of the object. The simulators are selected based on the complexity and availability of the vehicle model and the feasibility for the customization of vehicle models and working terrain. Customized applications require specific vehicle model. If they are not available, they can be modeled using tools like Blender. This is a typical example where we have modeled the excavator. The working environment shall support the essential features of the operation by the vehicle. For example, for modeling the digging action of an excavator, the environment shall be diggable. Rigging of model is done by customizing the bones and joints of the model. Good expertise is required for conceiving the maneuvering of the vehicle parts and the vehicle and its mathematical modeling. Another factor is the selection of sensors. On-weather day-night operations demands complex perception solutions with special consideration for the sensor usage. As we know, camera is very good for the classification applications, whereas the LiDAR has a moderate classification support, whereas the radar is having the poor classification support. But in the case of resolution, camera is having very good resolution, but LiDAR is having a moderate resolution, and the resolution is very poor for the radar. And especially for the off-road solutions, LiDAR is a preferable solution for that type of environment it is facing. Sensors shall be modeled as per their specifications. Resolutions, scanning rate, scanning patterns are to be replicated. While standard models of LiDARs are available, customization or remodeling would be required for the MEMS types of sensors. Another factor we need to consider in the sensor modeling is the scanning pattern. The scanning beams of the sensors may be in yaw plane or pitch plane, giving out different types of staining pattern. And here we are showing two examples. One is the scanning is done in the yaw plane, and the pitch will be varying occasionally in a slow rate. Whereas in the second case, the scanning is done in the pitch plane, and occasionally the yaw angle will be varying. And this sensor models will give a different type of streaming output. And that is very much important for the optimization of that. Then comes how to model the use cases. The use cases shall be modeled as per the test plan. The ROS integration and the animations can help implementing the maneuvering of vehicle and its interaction with the environment. Another important factor we need to consider in the development stage is how to format and store the sensor data. The sensor data can be in the raw data form or in the processed form, depending on the module under test consuming the data set. The noise shall be added to the ground truth data at an appropriate level to create the sensor data. The storage requirement is a challenge considering the huge data set and the huge number of test cases. Now, moving on to the discussions on the solution concepts. The main focus is given to the perception, localization, and mapping. The solutions for off-road vehicle can be grouped into two: the autonomous vehicle solutions and automated implement solution. The key enablers for these solutions are perception systems, localization, guidance and navigation, drive-by-wire systems, vehicle controllers, etc. In similar lines, the implement subsystem also has building blocks of perception, localization, control-by-wire, and controllers. The key solution areas are perception, sensor fusion, object detection, classification, tracking, localization, planning, and motion control, then implement control and vehicle control. In the case of environmental perception, we have technically sound camera-based solutions for object detection, classification, thematic segmentation, and tribal path detection. For many use cases, LiDAR-centric solutions are necessary for the off-road solutions. Our solutions cover object detection, class proposal generation, segmentation, localization, odometry, etc. A data analysis sensor fusion framework can meet the homogeneous and heterogeneous fusion requirements of off-road solutions, accepting different sensor types, different sensor counts. It supports sensors like LiDARs, cameras, radars, and other proximity sensors. The fusion can be done at different levels, like low-level raw data fusion to high-level information fusion. Localization is an important step to proceed with autonomous navigation. We have seen that localization is a bit challenging for the off-road segment. Data Resi has LiDAR-centric localization and solutions. Those are suitable for off-road vehicles. Typical solution for the map generation framework is shown here. The solution is meant for reducing the data volume and for speeding up the post-processing. While the LiDAR data is used as a source of feature points, other sensors like IMU, GPS, etc. help optimizing further. The concept for optimization of map generation from PCD to the feature points is illustrated here. The segments are selected first and the key feature points are extracted from the selection. Continuing on mapping and localization, this illustration shows the relative timing of the algorithm modules. The map generation can be at a lower rate compared to the perception and localization. And the solution is suitable for reducing the resource utilization. This blow diagram shows the existence of localization and mapping along with other vehicle subsystems. The feature selection is optimized based on the detections from perception layer. This will help eliminating the temporary objects from the map. The motion tracking data from the sensors like IMU, GPS, and wheel speed data, steering angle data can optimize the performance of the algorithm. Considering the solutions having remote applications, ecosystem of building blocks are shown here. The major groups are vehicle systems, infrastructure systems, personal devices, remote control station. The infrastructure solutions acts as extension to the perception system of vehicle with V2I and cloud connectivity. The personal devices provide interfaces for the simple controls and for receiving alerts and warnings. The remote operation solution can host applications for the mission management, diagnostics, data analysis, predictive maintenance, user interface, etc. The remote applications have components for the mission management for single and multiple vehicles, synchronous operations, platooning, and material management. Remote solutions can host components for the health monitoring, predictive maintenance, and diagnostics, and the connectivity requirements for the cloud application. Remote control of semi-autonomous operations can also be part of this framework. To summarize, autonomous off-highway vehicles market share is growing high. Autonomous operations can be deployed in use cases applicable in construction sites, farming, mining, and industrial sites. Tata is aware of the challenges associated with the use cases and the development activities and has solution approaches to handle them. Our major solutions are driver assistance applications, connectivity solutions, IoT cloud V2X 5G and all, then localization and mapping, then sensor fusion, then AI ML based object detection, classification and tracking, vehicle control and intelligent automation, and sensor fusion, diagnostic and predictive maintenance. The highlights of our solutions are like they can be optimized for various platforms. They are modular in nature. Other services are validation and simulation for the off-road segment. Let's watch a video on our off-road solutions.